Good day, ladies and gentlemen, and welcome to another edition of Prometheus University. Today we will be discussing the fifth part in our 9-part series, by the way, on bending stress analysis and design, beam stability, right? Beam stability part A, discussing buckling. Now, let's do a quick recap on what we have done up to this point in our first 4 videos. We have discussed essentially beam analysis and design from a stress and strain point of view. So if you go back and you watch the first 4 videos, you would understand what I mean. But a high-level overview here would show that in our first video, we developed what bending actually is, the compression and tension couple, and came up with the section modulus, which is a cross-sectional property that describes the distribution of bending stresses in the elastic range. And with the section modulus, we can come up with the stress in a beam as a result of a torque that we have in a particular segment of that beam. Or conversely, we can come up with the torque in a particular segment of a beam if we know the stresses that that particular section is experiencing. So if we know the yield stress of a beam, we can come up with the maximum moment that we can put on it. So that was our discussion in the first part of the 9-part series. Go back and watch that video for the derivation of the section modulus. In the second part, we came up with the moment of inertia. This was a deep dive into the concept of moment of inertia, which is not a simple concept by any means. I would advise you to go back and watch that video to refresh yourselves on that concept. But essentially, the moment of inertia has to do with the resistance of the cross section of a beam to rotating. And this resistance is dependent upon the distribution of the area with respect to the neutral axis of the beam. And this also has to do with bending and bending stresses. Again, watch the video in order to refresh yourself and see the explication of those ideas. In the third video, we talked about deflection, that is, rotation and displacement of beams. So we have a beam, we know its material, what material it's made of, and we have a certain amount of torque that we've put on it, a certain amount of loading that we've put on it, and want to see, well, how many inches does it deflect, or how many radians does it rotate at point A or point B or whatever. And using ideas which we developed in the previous 2 videos, we came up with the beam deflection theory, right? So far, as I mentioned, we're looking at beams in terms of stresses and strains. In other words, stresses and deformations. In the 4th video, we talked about the plastic section modulus. And the plastic section modulus gives us the ultimate moment that we can put on the beam, the ultimate torque, which will completely yield the entire cross section of the beam, right? So if I have a particular shape, I can know how much moment I can put on it before the entire shape yields, right? Now, stress and strain, however, are not the only issues to consider when analyzing or designing beams. Another important issue to consider is stability. And stability in this case has to do with buckling. Now, buckling is a term that we have definitely heard before, and we have some intuitive feel for. But let's refresh our memories on the term. Now, buckling is something that has to do with compression. And this is what I mean. Imagine, or go ahead and grab a ruler in front of you, a plastic ruler or a metal ruler with sufficient length, and place it in compression. Press down on it with your hand and on the top and on the bottom. And what will happen eventually is it'll go from the blue shape to the red shape. It'll buckle. before it yields, before you completely destroy the material or anything, it will buckle. And hence we say that buckling is associated with compression. So how come we're talking about a compression phenomenon when we're talking about bending? But if you recall, bending has to do with compression and tension. Therefore, buckling is associated with the portions of the beam in compression. So if you have a beam in positive bending, it's making the smiley face as we can see here on our red diagram. Then the top portions of the beam are in compression, and those parts are therefore subject to the laws of buckling, if you will. Now, in this video, we're going to focus on buckling in terms of a pure compression application. In other words, point 2 here, which says that bending involves tension and compression, therefore buckling is associated with the portions of the beam in compression, only gives us, explains why we have a warrant to talk about buckling, right, in analysis of bending. But we're going to now segue for a moment and just understand the phenomenon of buckling from a pure compression perspective. And in our next video, we will look at a phenomenon called lateral torsional buckling, right? Which has to do with the buckling of the portions of the beam in compression, right? Which is the kind of buckling that is associated with bending. We'll talk about that in the next video. But in order to do that, let's first of all talk about pure compressive buckling. What we're going to do next is try to understand what gives a particular structural member, right, a column, a compressive member, buckling strength. In other words, what makes one particular column less likely to buckle than another. They're both made of the same material and so on and so forth, all other things being equal. What makes one column less likely to buckle than another? Well, I think we all can intuitively point out that it has something to do with its slenderness, right? If they have the same length, but one is skinnier than the other, then it's going to take more force to buckle the less skinny member. So if we look at these two members here, one of them has thickness T and the other has a thickness big T. The question is, or what we're imagining is, that P1, which is the buckling load on the one with big T width, is much greater than P, or will be greater than P, in a way that's proportional to the thickness of the beam, in a way that's proportional to the difference in the thickness, right? So this is one thing that we can say, therefore, about buckling, that the bigger the cross section, the higher the buckling load, right? And that's intuitive. Secondly, we can create another parameter which has to do with its length. Let's say they're both equal thickness, right? They're both equal thickness, but one of them is much longer than the other. We can imagine, or we can even test, if you have two rulers, same thickness, same material, without even testing it, you can tell that the shorter one will require more load to buckle, that the more slender, taller one will buckle quicker, right? So the buckling load P, right, is less than the buckling load P1 in this case. Okay, so far we can follow. It's something that we have an intuitive feel for. We've been exposed to the phenomenon of buckling just living on planet Earth for as long as we have. So nothing strange so far, right? Okay, so we can say that the longer the length of the column, the lower its buckling load, right? Let's take it a little bit further and look at the cross section of the column, right? So let's look at this in 3D. So we have a cross section of depth big D and of width little d, right? And we're going to ask, in which direction does the buckling occur, right? Which direction does the buckling occur? Now, intuitively, we know, and you can test this with your ruler, that the buckling is going to occur in the manner shown to the right, right? It's going to buckle in the direction of little d, right? So we can say that buckling occurs in the direction where the cross section has the least moment of inertia, measured in terms of the radius of gyration. Now, the radius of gyration is something that we'll get into defining later on. The radius of gyration basically is the moment of inertia divided by the area and the whole thing square rooted. So it's the square root of the moment of inertia divided by the area. We'll talk about exactly what the radius of gyration is, but it's just another way of measuring the moment of inertia, measuring the distribution of area with respect to the neutral axis of the cross section, right? So, to reiterate, number 5 says that buckling occurs in a direction where the cross section has the least moment of inertia, measured in terms of the radius of gyration. So far, none of this is foreign to us. None of this seems like it's coming from a different universe. We've all experienced this stuff, and it's stuff that we could intuitively answer, right? Last thing to mention here, item number 6, is that buckling depends on the elastic modulus of the column. And this is something also that we can intuitively determine. If we have a steel column versus a plastic column or a wood column, we would expect that all things being equal, they have the same length, they have the same cross-sectional moment of inertia, and so on and so forth, that the steel column will require a lot more load to buckle than the plastic column, just because of the fact that the steel column is stiffer, right? It has a higher modulus of elasticity, okay? And modulus of elasticity is something that we've touched upon over and over again in our videos. The 7th and final parameter that affects the buckling load of a column is not very intuitive, and it has to do with the support conditions at both ends of the column. And by support conditions, I mean, is it pinned, i.e. free to rotate at the support locations, or is it fixed, held in a vice grip and not free to rotate and not free to translate either at the support locations, or is it free at one of the support locations, right? The combination of supports both at the top and the bottom of a column, pinned, fixed, or free, and whatever combination thereof, affects the shape that it creates when it bends. This affects its stiffness inherently, which in turn affects the buckling capacity. This is not very intuitive, but let's take it one step at a time. The ideal condition, which we have here depicted to the right, is a pinned column, a column that is pinned at the top and the bottom. When it buckles, it is free to start rotating right at the point of support. So it creates this nice, clean, bent shape that we see. And we say that it has an effective length of 1. The effective length factor, which is referred to as K, is the parameter with which we use to represent this variable that affects the buckling length. This variable being the support conditions, right? So let's take this step by step. What if we had a column that was fixed at the top and the bottom? What we can see here is that we have changed the shape that it takes when it bends, because we have constrained it, restrained it from bending, or from rotating, I should say, at the support locations. So we have thereby reduced the length of the column that is available to bend and buckle, right? And in this case, we are showing that we've reduced the length by half. So we say that a fixed column, a column fixed at the top and the bottom, has an effective length of half. The effective length factor would be 0.5. So in essence, this column will act as though it was half the length of the pinned column, right? Same column, same material, same cross-sectional properties, same length. But if you fix it and constrain its ability to rotate at the support locations, it'll act as though it was half as tall. Okay? And we know from number 4 that the longer the length of the column, the lower the buckling load, right? So therefore, the shorter the length of the column, the higher the buckling load. A shorter column is stronger in buckling. But we'll find out next from the Euler load, and because Euler did empirical studies on this and came up with an analytical formulation for dealing with all this stuff, we'll find out the exact proportionality. And it turns out to be that the buckling stress is proportional to the inverse of the length squared. So in this case, where we have effectively made the column half as tall, we have increased its buckling strength by 4 times. If we make it twice as tall, we've reduced its buckling strength by 4 times. Okay? So let's look at another support condition. In this support condition, it's fixed at the bottom and it's free at the top. And again, the shape of the bending is different. Therefore, the stiffness is different. And in the way in which we express this, we would say that its effective length is different. If you see here what I have drawn out in red to join the black dotted line, it is bending as though it were twice its length. It is essentially behaving as though it were twice as long as the pinned column. Hence, this column will be 4 times as weak in buckling. Okay, so as I said, this is not very intuitive, but if we do experiments, we can find out. We can pin this ruler, hold it free to rotate, and then try to buckle it. We can put it in a vise and try to buckle it. We can leave one end free and then push it down and try to buckle it that way. And we will see that the shape of the buckling varies, all right? And the way in which we conceptually capture this is by using the effective length, which I have just described, right? And to reiterate, the pinned column top and bottom is the ideal. If we fix it on the top and bottom, we have reduced the length available to bend by half, thereby making it 4 times stronger. If we have it free at the top and we have the bent shape look as though it were twice as long, we have made it 4 times weaker. Okay? Now let's get to that equation that shows the proportionality of all these things. Our friend Euler, who did a lot of work in mathematics and engineering, did a bunch of empirical tests, varying all these parameters which we've talked about, right? And just to go through the parameters again, we said that the bigger the cross section of the column, the higher the buckling load, right? And also that the longer the length of the column, the lower the buckling load. These two taken together, number 3 and number 4 taken together, are known as the slenderness. Okay? Basically, the slenderness has to do with the length and also the resistance of the cross section to bending, right? Buckling occurs in the direction of the cross section with the least moment of inertia. Okay? That's looking at it in a 3D view, seeing which way the buckling will occur, right? And also we know that it depends on the elastic modulus, right? Now, upon doing his tests, he came up with a buckling stress. You have these various columns, you put a stress on them, and at some point they'll buckle. What is that number, and how does varying all these parameters affect that number? And he came up with the Euler buckling stress, which we see here. Pi squared EI over AL squared. And as we can see here, It has to do with the elastic modulus. I is the moment of inertia. And then it is proportional to the inverse of the length squared, right? So the longer it is, the weaker it is. Okay? In a geometric, or shall we say quadratic way. So another way of looking at this equation is the way in which it's highlighted in yellow, right? It takes out the moment of inertia and the area and replaces it with the radius of gyration. In the denominator, we have L over R, and that is called the slenderness ratio, which has to do with item number 3 and 4, right? The resistance of the cross section to bending and the length of the member itself. These things affect the buckling, right? If something is more resistant to bending, it makes it such that it's more resistant to buckling. And this resistance to bending is represented by the radius of gyration. If something is longer, it is weaker in buckling. It is more susceptible to buckling. And we can see there, as it's represented in the numerator, that makes sense from this equation. Also, we can see that the higher the elastic modulus E, which is on the numerator, the more it is stronger in buckling, to say. The stronger the buckling stress. Okay, now we have explored buckling in pure compression. And in the next video, we're going to talk about lateral torsional buckling, which has to do with the compressive portion of the beam that's in bending. So as we said in item number 2, bending involves tension and compression, therefore buckling is associated with the portions of the beam in compression. A beam in bending is subject to the laws of buckling in so much as a portion of it is in compression. So we can imagine if we have a beam that's long enough, but the length, it has such a length between the supports and such a length between the lateral bracing, and it has a certain radius of gyration, right? And we put it in bending, and there's a certain portion of it that is in compression. It's going to reach, that portion is going to reach a buckling stress, right? Which is not exactly this buckling stress that we see. It's not exactly going to go in this manner, because over here we're looking at the entire cross section, but for bending only a portion of the cross section is in compression. But by looking at this, we can understand that at some point there will be a buckling stress that is reached, right? And that this compression portion of the beam will buckle. And that we will explore when we explore lateral torsional buckling in the next video. Well, thank you very much, ladies and gentlemen, and thanks for your time. And if you enjoyed this video, please go ahead and subscribe to our page and share it. And please look out for the next part in this 9-part series in bending stress analysis and design, when we will be talking about the second part of beam stability, lateral torsional buckling.